Welcome to the first episode of linear algebra. Now, we already did an episode of linear algebra, sort of. That was like kind of review. But the thing about it is, I waited such a long time in between those two episodes. So for you guys who've been waiting for the first episode, I'm really sorry. I've been busy with some other stuff that I cannot disclose. Actually, I can. It's just university admissions, but and family problems. But anyways, we are going to be doing the linear combinations today. We are going to um start linear algebra. Linear algebra starts with linear equations, and you've probably already seen these equations. This is called the standard form of an equation. Um, in middle school linear math, you've seen this before. A times x plus b times y plus c is 0, or ax plus by equals c. I think we'll mostly deal with the second part, the second thing more than the first thing. But what makes these equations linear is that you can scale something by a factor. So if you have some variable x, you can scale it by a factor c. That's that is a scalar. The c is called a scalar, and that is allowed in the linear expression. If I can draw a good C, that is. You can also add two terms together. So how would that work? Well, it's just x plus y, right? So that is allowed under the linear classification as well. And what else? What else is allowed? You can scale and add them at the same time. So you can do cx plus dy, and that is usually what you'll see in linear equations. Um, you will see something like 2x plus 3y equals 5. That's a linear equation. If you see something like 3xy equals 6, that is not a linear equation in terms of x and y. If it's independent of each other, then 3xy equals 6 is not a linear equation if x and y are separate variables. So that is what you have to be careful of. So which one of these are linear? Well, so for vectors, instead of numbers or instead of just variables representing one number, it can represent more than one number. That's a vector. It has a magnitude and direction. But we usually deal with their component forms, which is one, or in this case, it's 1 to the right and 5 up for this vector, and 2 to the left and 3 up for this vector. So we usually deal with their component forms that deals with which direction they go right, which direction they go up, and whether or not they're negative, so they'll go the opposite side, or not. So are these linear combinations? Let's see. So the first one is 2 times a vector plus 3 times a vector. Yes, linear combination. E squared times a vector plus a vector. Is this a linear combination? There's a squared in it. It is. It is a linear combination. Why? Because e squared is a constant. It can be any constant. It's not like vector squared. It's just e squared. So that is a linear combination. Now, what about 2, 5 plus -4, 3. You can add two vectors. So yes, linear combination. What about the last one? The vector v minus the vector -4, 6. That is also a linear combination. They're all linear combinations. I don't know why I didn't put a non-example in there. What would be a non-example? A non-example would be v squared minus w squared. That's a non-example. What else would be a non-example? Vw minus wb. That's a non-example. And in fact, this is a little bit strange of a notation. I would not write it like this. I also wouldn't really write it like this either. But that's why they're not linear, because we're playing linear algebra. We are studying linear algebra, not the multiplication of different vectors that we don't know. That's not linear. So These are all linear combinations because they involve a constant or a non-constant, not a constant, times a vector plus another constant times a vector. It can be known, it can be unknown, whatever. It is still a linear combination. All right, so this is a little. It's gonna be a little bit harder. It's just gonna be solving equations, but let's see. So find the linear combination of v and w that will v and u that will produce the vector r, and the r is 1, 6. If this. So what is the linear combination? Well, let's find out. So c1 times 1, 3. Right. This is our setup for the linear combination. C2 times 0, 3. That's our setup for the linear combination. It's just constant times a vector plus a constant times a vector. So what combination of these two vectors will produce you the 1, 6? Now you can actually just notice by inspection what the correct answer will be. But I'm not going to do that. I'm not going to make you notice. I'm going to actually solve this out for real. So what can you do? You can multiply scalars into vectors. So how would that work? C1 times 1, C1 times 3. It's like a distributive property, sort of. So what you'd get is C1, 3C1 plus C2, or I'm sorry, 0, 3C2 is 1, 6. So what does this mean? Now you can add them together. You can add their components. So you'll get C1, 3C1 plus 3C2 is 1, 6. So just by equality, the tops have to be equal to each other and the bottom have to be equal to each other. So what does this mean? This means that C1 has to be 1 and 3C1 plus 3C2 has to be 6. So C1 is 1. So if you put 3 plus 3C2 is 6. C2 is 1. And that is your answer. So the linear combination is 1. If you were to rewrite it, it would be 1. I hope that's in the screen. Nope, it's not. Okay, so 1 times 1, 3 plus 1 times 0, 3 is 1, 6. That's how you would write it. These are column vectors. I could use row vectors, but I don't want to. So yeah, that's how you solve the first question. Now, the second question's harder. If I can actually move the thing, please, please, please let me move the thing. C2 equals 1. There you go. Anyways, let's start the next question. The question is, now we have to take the combinations of these two vectors. So these are a little bit harder. C1 times 2 minus 5 plus C2 times minus 1, 4 will give you the 1, 6. So if we've established a pattern, we can just use that pattern from now on. So we can actually just convert this into the systems of equations that we want, which ends up being 2C1 minus C2 is 1, right? Because if you multiply C1 by 2 on top here, you have 2C1. Multiply C2, you have minus C2. 2C1 plus negative C2. 2C1 minus C2 is equal to 1. And minus 5C1 plus 4C2 is 6. So this will end up very messy. This will end up very messy. I don't even know if there's a right solution for this. I'm going to be really honest. But we can multiply the first, we can do substitution or we can do elimination. I'm going to do elimination because that's what we're going to be doing for a really long time. So we're going to multiply the first equation by 4, and I'm just going to put it down here. 8C1 minus 4C2 is 4. Add them together, 3C1 is 10. So C1 is 10 over 3. So if C1 is 10 over 3, we can plug it back into the equation. Probably the first one will be the best. So 2 times 10 over 3 minus C2 is 1. So minus C2 is 1 minus 20 over 3. So C2 is 20 over 3 minus 1, or 17 over 3. So how you'd write this is 10 over 3 times the first vector plus, or 10 over 3. You could also write it as just 10 over 3 times v plus 17 over 3 times u is equal to r, or 1/6, whatever. And that's the linear combination right there. It's c1 times v plus c2 times u is equal to r. Now I kind of want you to. What we've been doing is a little bit arbitrary. It's quite arbitrary. So what I kind of want you to do is think how this could be represented onto the coordinate plane. So what does this mean? Well, the linear combinations, or the c1 whatever, whatever our c1 is in a 2D plane, because we have two vectors for now. If we have c1 and v1, and we could change c1 to however we want, that will span, and that's vocabulary that I probably shouldn't use, but that will determine a line in the plane. Why? Because if you have a 3 comma 4 like this, right, 3 comma 4 like this, if you shrink it in half, you'll have it like this. If you make it negative, you will have something like this. It will span the entire line. There's vectors, infinitely many vectors, and it can point to any vector or any point in the line. And that is the linear combination of one vector. So if you have a linear combination of two vectors, now you can add to the other vector. This one you can only scale because you're not adding anything because you only have one vector. You can only scale the vector. That's the only operation that's allowed under the linear that we've established. But with two vectors, you can add to the other vector now. Now, by adding, you can actually determine the entire space like this. And the yellow is the space. The yellow is the entire space of R2. R2 being the plane, the xy plane, where x is all real numbers and y is all real numbers. That's R2. So you can determine the entire plane using two vectors. Not always, almost always. When can you not determine the entire two-dimensional space? I'll let you guys think about that. I'll probably reveal the answer in chapter 2, which will be long ways away, but we will discuss that. So we can also express a linear combination of three vectors. Now, three vectors is going to be a little bit ugly, but not for this first question, but for later questions, it will be a bit ugly. But for now, we'll express linear combinations like this. So C1, now we have C1 U1 plus C2 U2. So you have C1 times 1 0 0 plus C2 times 0 1 0 plus C3 times 0 0 1 is equal to 0 2 0 negative 2 1. Alright, and I use angular brackets, but sometimes you also see it just like a coordinate, like an actual parentheses, like that. Sometimes it's used like that in linear algebra, and you got to be aware of that. So what you'll end up with is, this is called the standard basis. Why is it standard? Why is it a standard basis? It's because 1 0 0 is a vector that's 1 in the x direction. 0 1 0 is a vector that's 1 in the y direction, and 0 0 1 is a vector that's 1 in the z direction. So it's literally the xyz plane you've been working with in Calc 3. It's just, or the xyz plane you work with in, I don't know, Algebra 2, pre-calculus, but it is a standard plane. Now, you will see bases, you will see ways that people define coordinate systems that are not intrinsically standard in linear algebra, and that can be very useful, or it can be very annoying. Um, it will be useful in later applications of computer science and physics. But for now, we're just trying to study, we're trying to get this down. So let's see what would happen. So I think you guys probably already know which how like the combinations that it takes to get this vector, because this left hand side will just end up being c1, c2, and c3, and this is equal to 0, -2, 1, right? You guys might say, why don't we do this all the time? Well, sometimes the world doesn't work like that. Relativity comes in and messes up our coordinate systems, and we have to define the new coordinate system in terms of the old coordinate system, um, which is one of the kind of main one of the heart ideas of linear algebra is that we can define new coordinate systems in terms of old coordinate systems. What will happen with that? How do we do it? How do we find out what happens? And what do certain values that we determine from those transformations mean, like the determinant? So anyways, I'm just getting too I'm just getting ahead of myself. But this is the combination. Now what about this? All right, this is the last question. So, now it's a little bit harder. So C1 times 101 plus C2. This is not a standard basis. This is a non-standard basis. But one of our values is still one of our vectors are still standard, but it's not standard. It's not a standard way of defining the XYZ plane. The standard way of defining the XYZ plane is vector in the X, vector in the Y, vector in the Z, and they're all unit. They're all one. These aren't. So they're going to be a little bit harder, but we can still express them as a linear combination. So this is 0 minus 2, 1. So you can actually write the system of the equations right now. I'm going to do that. So C1 plus C3. For all the tops, it's C1, 1 of C1, and 1 of C3 is 0. C2 is minus 2. And 1 of C1 plus 2 of C2 is positive 1. So what does that mean? That means, well, we can just take this C2 equals minus 2, substitute in here, back substitute. So C1 minus 4 is 1. So C1 is 5. And C3 is, well, 5 plus C3 is 0. So C3 is minus 5, or negative 5. So that means, what? That means 5u1 plus, or no, not plus, minus 2u2 minus 5u3 is equal to 0. No, not 0, sorry. 0 minus 2, 1, so W. That's it. That's the first lesson. Linear algebra is going to be easy for most of you guys. And the reason it's going to be easy is because you've been working with logarithmic equations, trigonometric equations, calculus, and then you see this, and then it's like a joke. It's seriously easy. But you will not get bored because it will get harder, um, and it will force your mind to think in many different ways you've never thought before. Um, I will see you next time.